So today we're going to continue with electron configuration, and we are going to start with the longhand configuration of lead, Pb. And if we identify where lead is on this chart here, I believe that is where lead will be. Yep, in the 6th row. Okay, so we start at the top, 1s, go to 2s. 2 boxes, so it's 1s2. Go to 2s. 2s2, keep going, 2p, count the boxes, 6, 3s, count the boxes, 2, keep it going. This is getting a little boring and repetitive. 4s2. Next one, 3d10. If you know what you're doing and you want to move ahead, you can, but slow down because you want to see what happens with the f's. 4p6, I'm going to go through all of these right now. 5s2, 4d10, 5p6. Now it's a little tricky. 6s2 is straightforward. And when I go across this right here and I keep going all the way across, that means I've also got to include my 4f's. If you look at your periodic table, you will notice that in the atomic numbers right here, it skips 14 by 14. So different periodic tables do this differently, but there are 14 actual elements between these two elements in most periodic tables. So for the electron configuration, we have to write 4f14, 5d10, and then we have to go up to and including lead, 6p2. And that is the longhand configuration, electron configuration for lead. Let's figure out what the shorthand configuration would be. So first thing I have to do is identify the noble gas 1 row above lead. Those are our instructions. And the noble gas 1 row above lead is xenon. If you look at your periodic tables, that is xenon right here. And if you want to try this on your own, pause. It's going to appear very shortly. So we put xenon in brackets. And then I still have to include all of the electrons up to and including lead. So 6s2, 4f14, 5d10, 6p2. That would be the shorthand configuration for lead. Now let's talk about electron configurations for ions. So if we were to do the electron configuration for S2-, first you want to figure out where is S on this periodic table. So sulfur is right here. Oops. Sulfur is right here. And S2- means we have extra or too few electrons. You want to think about that for a moment. Pause if you need to. And S2- means we have 2 extra electrons. Negative charge means extra electrons. So when I do the configuration, instead of going only to sulfur, I actually have to add 2 more electrons to my configuration. So I'm going to do the longhand. 1s2, we're just going left to right, top to bottom. We're going to go all the way to right here. So 1s2, 2s2, 2p6, 3s2, 3p6, and there's my configuration for S2-. All right, how about Ca2+? Oops, sorry about that. Okay, calcium is right here. The calcium 2+, extra electrons or too few? Think about it for a moment. Pause if you need to. I'm about to tell you. It means we need to take away 2 electrons. So that means these 2 electrons we are not going to include in Ca2+, because a positive charge means you've lost some electrons. We do the same thing. We write the configuration. I'm going to do it the longhand way again. I have to include all these electrons. I don't include those 2 electrons. Why not? Because I have Ca2+. So 1s2, 2s2, 2p6, 3s2, 3p6. Ooh, look at that. What happened there? Do you notice that These two ions have the exact same configuration. Huh, what does that mean? We have a term for this. It's called isoelectronic. If two atoms are isoelectronic, it means, hold on, so two atoms or ions have, it means they have the same electron configuration. Iso means same, electronic. Same, iso, electronic, same electron configuration. And there's one more little interesting tidbit here, which is that, which is the shorthand configuration. So notice for this S2 minus right here, I ended at the end of a row right here, 3p6. So it's kind of like I ended at a noble gas. I could write the shorthand configuration for S2 minus as argon in brackets. That means S2 minus has all of the electrons that argon has, no more, no less. Ca2 plus, same thing. I could just put argon in brackets for the shorthand configuration for calcium 2 plus. And that's it. End of story. Oh dear. Okay, so you do these on your own. You're going to pause in a moment. Don't pause yet. I want to say a couple quick things about these. Just be careful with the ions. Remember whether or not to, oops, that's not an ion. Remember whether you're supposed to add or take away electrons. And don't forget, if you end at the very end of a row, when you add or take away electrons, you can use the shorthand and just put that noble gas in brackets. I'm going to do just the shorthand configuration for the answers. Go ahead and pause, and in a few moments, all the answers are going to appear. So hopefully you paused. Pause, pause, pause. All right, so here are all of your answers. Oh, goodness. Here's all your answers. And if any of them are looking strange or you don't know what's going on, you know, email me a question and hopefully I will send it back to you and I'll put it in the comments section. You would just want to notice for the Bi3 plus, I took away these 3 electrons. For Sr2 plus, I took away those 2 electrons. Cl1 minus, I added an electron, and that got me to a noble gas, so I could write that in the shorthand form. And the nitrogen, I didn't bother writing it in shorthand because it would take the same amount of time as just writing the 1s2 in there. Why isn't this? All right, so we're going to start looking at orbital diagrams. And we use the electron configuration to draw orbital diagrams. And this is just a visualization. Instead of just seeing a linear 1s2, 2s2, 2p6, orbital diagrams show you separately where electrons are located. And we'll notice some important features here. Energy increases as we go up. And there is no x-axis. We don't worry about the x-axis here. All of the 1s here, they're all aligned. That's not necessary, but often we align the s's, we align the p's, and we align the d's. The important piece here is, you'll notice, 3D, that sublevel, has more energy than a 3p, which has more energy than a 3s, which has more energy than a 2p, more than a 2s, which has more than a 1s. More energy. Okay, let me show you how to fill these in. So we will start with nitrogen. We saw in the previous slide that nitrogen, nitrogen has a configuration 1s2, 2s2, 2p3. So 1s2, 2s2, 2p3. What is this here? We'll close that keyboard. Okay. So we need to put all these electrons into the orbital diagram, and the rules are, oh dear, we'll write out our rules. All right, so here are our rules. We have to fill a row before moving up a row. And within a single row, we have to put one electron per orbital before we pair electrons. You'll see what that means in a moment. So we're doing nitrogen. You want to figure out how many electrons you need to put into your orbital diagram. And for a neutral atom, the number of electrons you're going to put in there is equal to the number of protons, just for neutral atoms. So I need 7 total electrons. And electrons we draw as little arrows pointing up or down. So I'm going to start counting. 1, 2. I'm allowed to put 2 electrons per orbital. These little lines are orbitals. They each represent 1 orbital in a sublevel. So I'm at 2. I have to get to 7. I filled a row, I can move up. I filled my row, I can move up. 3, 4. I filled a row, I get to move up. But now, in this row, I have to put 1 electron per orbital before I can pair the electrons. I'm going to go 5, 6, 7. When you start putting electrons into an orbital in a sublevel, you must point all of the electrons in the same direction. So, I could have put the electrons this way, or I could have put them all facing down. It doesn't matter. I just tend to always start with an up arrow as opposed to a down arrow. And an arrow represents an electron. The up just represents an electron spinning in one direction. The down arrow represents an electron spinning in another direction. And I haven't told you this before, but electrons do have a spin. They spin on their axis. And now I'm going to do nickel. And nickel is number 28. So I need 28 electrons. So I have to follow my rules. I fill a row before moving up. So 1, 2, I get to move up. 3, 4, I get to move up. 5, 6, 7, I put 1 per orbital in a row before pairing up. 8, 9, 10, now I can move up. 11, 12, and I can move up again. 13, 14, 15, 16, 17, 18. The 4s is actually above the 3d. I'm not sure what happened here. 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Okay, that is the orbital diagram for nickel. Okay, and I made a little point there. I got this orbital diagram online, and the 3D is, oh wait, yeah, the 3D is above the 4s. It should not be below the 4s. That's very strange. So let's just make a note that these electrons have more energy than those 4s electrons. And the 4d electrons have more energy than the 5s electrons. This orbital diagram that I got online is not actually correct. So I'm going to find a new one for the next problem. Okay, I found a much better orbital diagram online. That took a while. I had to do a little bit of editing there. And you'll notice that in this particular one, the 3D has more energy than the 4s, and that is shown correctly. So this particular orbital diagram right here has the correct energy amount for each particular orbital. And I want you to try filling in all the electrons for bismuth, number 83. There is no shorthand method for doing this. You have to do all 83. So I want you to pause your video right now, and I'm going to fill in the 83. But you should do it on your own. So pause. Okay, here I go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. What's next? The 4p's. 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43. This is getting boring. 44, 45, 46, 47, 48. Poof! 49, 50, 51, 52, 53, 54, 55, 56. Who's next? The F's. 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70. My gosh. None of the 5 D's. 71, 72, 73, 74, 75, 76, 77, 78, 79, 80. Next highest energy is 6 P's. 81, 82, 83. We're done. That took a while. I won't give you a lot of those. Don't worry. Now let's just do a quick comparison. If we were to now look at all these electrons in here and write out the electron configuration based on what I see here, I'm going to do that right now. In the 1s, I have 1s, 2 electrons. 2s, I have 2 electrons. 2p, notice, I have 6 electrons. And then the 3s, I have 2 electrons. I'm going to keep going. I'm going to pause though. Okay. If we look at the entire configuration here, we will see that this configuration right here, which is a configuration we get if we write out all of these electrons, is the same as the electron configuration for bismuth that we did earlier in lecture right here. It's this one right here. Notice it ends the same. 6s2, 4f14, 5d10, 6p3. Let's look over here. 6s2, 4f14, 5d10, 6p3. The orbital diagram and the electron configuration should give you the same results. It's just that the orbital diagrams gives you a better picture of where the electrons are truly located. The electron configuration tells you which sublevel the electrons are in and how many. Remember, these numbers tell you how many electrons are in each sublevel. The orbital diagram lets you see how the electrons are filling into the shells. So in this 4f sublevel, I have 1, 2, 3, 4, 5, 6, 7 orbitals, and each orbital has 2 electrons. Okay, so now I want you to practice these 2 on your own. I'm going to fill them in. I want you to pause. Don't forget the number of protons is how many electrons go into the orbital diagram for neutral atoms. And these are neutral atoms. If we had ions, we would either add or subtract electrons. So you pause, and the answers are about to show up. And here are your answers. So now we're going to get into a couple more definitions. There's something called paramagnetism and diamagnetism. I'll write those down. So 2 new terms, paramagnetism, diamagnetism. Paramagnetism, very weak attraction to a magnet due to having unpaired electrons. Diamagnetism, it's much weaker than paramagnetism, and it causes a substance to be repelled by a magnet. And anything that is diamagnetic has all of its electrons paired. All the electrons are paired. Paramagnetism, you have to have at least 1 unpaired electron. So the key is whether all the electrons are paired or if there are any unpaired electrons. So let's go back and look at all of the orbital diagrams that we've looked at. You have to actually look at an orbital diagram to check for paramagnetism or diamagnetism. So let's see. Nitrogen has unpaired electrons. If you have any unpaired electrons, the substance is paramagnetic. Paramagnetic. So nitrogen, in fact, is paramagnetic. I can't speak today. Okay, how about nickel? Oh, I see some unpaired electrons right here. Therefore, nickel is paramagnetic. Nickel would be slightly attracted into a magnetic field or attracted by a magnet. Bismuth. If you want to pause, go ahead and pause and check all of them. I'm going to give you all the answers. Bismuth has unpaired electrons, so it is indeed paramagnetic. What else do we have here? It looks like everything has unpaired electrons. Unpaired, unpaired, everything is paramagnetic that we've looked at. But that is not true for all elements, and I cannot spell today. Paramagnetic. There we go. All right, so how do we check paramagnetism without having to do that entire orbital diagram? This is what we do. We only check the very last sublevel for an element. We count the electrons in the last sublevel. We draw the orbital diagram just for that sublevel, and we see if we have any unpaired electrons. So we're going to do a couple examples here. Okay, you're going to start figuring out sublevels without looking at that little chart that we were using in class. So neon is right here, and I know I'm in the second row of the periodic table. Oops, what's going on there? I'm in the, okay, I'm in the second row of the periodic table, and I know that these are p electrons, so I know that my last sublevel is a 2p sublevel, and I remember from class that 2p's have 3 orbitals. So this is my, quote, orbital diagram for the last sublevel. So I'm going to count how many electrons neon has. 1, 2, 3, 4, 5, 6, 2p electrons. I count the boxes in that section. And I'm going to fill them into my 2p sublevel. 1, 2, 3, 4, 5, 6. And I have to fill those in using the rules that I've always been using for filling in orbital diagrams. I put 1 electron per orbital before I pair up electrons. Now I check. Do I have any unpaired electrons? No. Therefore, neon is diamagnetic. Okay, if you think you have the hang of this, you can pause. If not, you can follow along. But first, just note, palladium's right there. So if you want to go ahead, you can pause. So I have to find how many electrons does palladium have? That was the first step. Count the electrons in the last sublevel. How many electrons does palladium have in here? Okay, 1, 2, 3, 4, 5, 6, 7, 8. I need to deal with 8 electrons. And what sublevel am I in? Well, let's see. We're in the 1, 2, 3, 4, 5. We're in the 5th row. And I remember that D's happen to always be, oops, it's not a 5D. D's are always 1 less than the row that they are in. So if I'm in the 5th row, these are 4 D's. Now D's, how many orbitals are there in a D sublevel? I remember there's 5. 1, 2, 3, 4, 5. If you ever forget, what you can do is count the total boxes in a sublevel and divide by 2. The D's have 10 total boxes, and you divide by 2 to get 5 orbitals. Okay, I have to put 8 electrons into this 4D sublevel. 1, 2, 3, 4, 5, 6, 7, 8. I have 2 unpaired electrons. Therefore, palladium is paramagnetic. Paramagnetic. Okay, I've written 2 problems. I circled them on the periodic table. I want you to pause, try these on your own. I'm going to pause and just fill in the answers. So pause. Okay, here's your answers. Did you get them right? Hope you did. Okay, very last thing, we're going to talk about outer or valence electrons. All right, so we already did these problems, 1 through 7, in the beginning of this video. So now we're going to look at outer or valence electrons for these problems. And outer electrons are the electrons in the outermost shell, the highest shell number. It's really important, the highest shell number, not necessarily the last sublevel that you fill in, but the highest shell number. So let's do these. Nitrogen, the highest shell number is 2. So the outer valence electrons for each of these samples. Sorry, I just filled in each different element. So for nickel, the valence electrons would be 2s2, 2p3. That's it, you're done. Nickel, and if you feel like you can do this on your own, go ahead and fill these in and pause the video. So nickel, the highest shell number is 4. I do not include my 3Ds. Nickel, the valence electrons, the outer shell electrons, 4s2. Number 3 we are not even going to deal with right now. We'll talk about it probably in class. Number 4, well, I've only got one shell number listed, 5s2. Number 5 we're going to skip. And again, pause if you think you know how to do these, and just look at the end. Okay, highest shell number. I've got my 6 S's and my 6 P's. So 6s2, 6p3. Now this ion we can do because something else happened. So for bismuth, the highest shell number is shell 6. I don't include my 4s, 4f's, or my 5d's. It's just 6s2. Do you notice something about all of these? What are the only kinds of orbitals that can be in the outer shell? S's and P's. We never include D's or F's because they always go into an inner core shell. So shell 1 is closest to the nucleus, shell 6 is farthest from the nucleus, and shell 5 is closer to the nucleus than shell 6. So remember, D's are 1 less than the row year that you're in, so you never include D's. F's, you might have noticed, but it's okay if you haven't. F's are always 2 less than the row that they are in. All right, that's it for today.